Swayam Prabha. Digital India. Educated India.
Hello everyone. Now our present topic is cone pulley in roving frame. We are continuing with roving frame part. So, cone pulley is very important part in roving frame where we get the variable motion. So, now we will try to understand here the mechanics of cone pulley. So, bobbin speed is a function of bobbin diameter, as we know, as the in case of say bobbin leading mechanism. So, V is the delivery speed, pi d is the bobbin diameter dV, n b minus n f flare speed. Okay. So, bobbin speed is a function of bobbin diameter. As bobbin diameter during building, bobbin diameter increases, that to keep the equation. So, to maintain this equation, so V is a constant, V is the delivery speed constant and spindle speed constant, so or flare speed. So, bobbin RPM has to reduce. So, that is why we need to change the bobbin diameter, reduce the bobbin diameter in case of bobbin leading mechanism, and this is done through cone pulley. So, we will discuss a detailed the mechanism of cone pulley, and cone pulley speed changes by shifting of cone belt, that we will discuss here. So, reduction of bobbin speed by cone pulley. So, winding each layer of roving, that is building mechanism shifts the cone belt, and speed of the top cone remains constant, but bottom cone pulley is reduced after every shift. So, from the bottom cone pulley, as we know, the drive is transmitted to the epicyclic gear. In last session we have discussed, and it is transmitted to the first the arm. It gives the drive to the arm, and from there the output of the epicyclic gear goes to the it is a bobbin. So, it uses the speed of the epicyclic gear. Let us see once again. So, this is the bottom cone pulley, okay, and from here the drive goes to the epicyclic gear, and this is the pulley which receives the drive from the bottom cone pulley, and this is actually the arm in the epicyclic gear system. So, this speed is superimposed. So, this variable speed is superimposed with the speed from the main shaft, which is the fixed speed, okay, that we have studied, we have discussed detailed in the last session. So, output from the epicyclic gear is transmitted to the bobbin through different gear system. These are the gear system. Okay. Now, so based on the space consideration, specially designed epicyclic gear is used. Okay. So, the dimensions of the following can be selected. So, maximum and minimum diameters of the cone. So, that there we cannot have very long lengthy cone drive. So, the diameter has to be selected, and the length also is the limitation. So, we cannot have very large size of cone pulley. So, this diameter of maximum and minimum diameter is the limitation. So, sum of top and bottom cone pulley diameters for any cone belt position should be constant, because we use a single belt. So, the sum of the diameter of the cone pulley top and bottom cone pulley should be constant, because we have a fixed length belt, okay. And that is why the, and also to keep these things, the both the axes of the cone pulleys, top and bottom pulley, should be parallel, okay. So, belt length is fixed. So, length of the cone pulley is also important. So, this cone pulley, for the sake of the space, so we have to shift the cone belt within a limited space. So, based on the dimensions of the following elements, the design criteria must be set. What are the elements? Width of the belt. So, belt width is also a limitation. We cannot have very thin, very narrow belt. So, very narrow belt will actually have slippage. To reduce the slippage, we need a wider belt, cone belt, but wider belt will limit the movement of the shift of the belt, the length of shift of the belt. So, we have to optimize the cone belt. With diameter of empty and full bobbin used. So, empty and full bobbin diameters are to be considered, because that the, if we want to have very large diameter, the problem would be that we have to shift the cone belt in a larger extent. So, that is not possible. So, we have, that is a limitation. So, that we have to decide, and this diameter, this shift, total shift of cone belt, and this thickness of the bobbin roving is also related. Simplifying the design approach. So, what are the following of points? So, what we are doing? We are actually assuming that it is a bobbin leading mechanism. So, in bobbin leading mechanism, universally adapted. So, all commercial machines are based on this at present, based on the bobbin leading mechanism. So, we will consider only the bobbin leading mechanism in our derivation. The length of the roving delivered by the front roller per unit time is constant. So, that is true, basically constant delivery rate, and also the flare speed is constant. So, that is why twist density along the length is constant, twist per unit length is constant. The roving diameter is assumed to be the very small, infinitely small, okay, and for a very accurate design of the. So, it is a there is a certain roving diameter should be there, and roving is considered to be incompressible. So, while winding there is no flattening, that is our assumption, because in actual practice roving is compressible, but in our assumption we are assuming it is basically these are the points. So, it is incompressible. So, no flattening during winding tension. Okay. Now, the cone profile, if we see, there are two types of cone profiles. One is the hyperbolic cone profile and another is straight cone profile. So, hyperbolic cone profile is basically it is required hyperbolic profile, because the if the shift of the cone belt is uniform after every layer, then to match the bobbin speed we need hyperbolic cone belt. So, bobbin rotation varies with the shift of the cone belt. Okay. So, this is due to cone belt drive and cone belt shift. Bobbin rotation should change the that rate of change of bobbin rotation should change, because for first layer if the bobbin rotation changes to a certain extent, but first to second layer, then it will be different. For every layer the things are there that the change of bobbin speed are not constant. Now, let us see with a simple example. Okay, this 2 millimeter is bobbin diameter and empty bobbin diameter is 50 millimeter. Now, after that first layer, so at the initial layer the bobbin diameter is 15, for first layer bobbin diameter will be 50 millimeter for the first layer. Now, let us see the second layer. So, after first layer, that is second layer, the diameter of the bobbin, this is in the for the second layer, diameter of the bobbin becomes 50 plus 2 multiplied by 2, that is in the both sides. So, it is increasing. So, 54 millimeter. So, there will be 8% increase in diameter. So, accordingly bobbin speed has to reduce by that proportion. Okay. And from first layer to second layer, let us see the in the second layer this becomes 58 millimeter. So, that means there will be 7.4% increase in the diameter. So, that if you see the rate of change in diameter after every layer is reducing gradually. So, to match this type of diameter, and so that accordingly the bobbin speed has to be changed. So, it has been observed, and mathematically also we have seen that this change in bobbin speed is in hyperbolic nature. So, to maintain these things, ideally the cone dimension, cone shape should be hyperbolic in shape, but there are some issues. So, shifting of belt if we keep constant, then definitely we need hyperbolic cone shape, that if we shift the cone belt in a constant amount does not change the speed as per the requirement. If we try to use the straight cone, in the straight cone if we shift the cone belt in a uniform constant amount, then we do not get the required change in the speed. Hyperbolic cone faces are used where concave and convex cones are used. So, that we can see here. So, here if we shift the cone belt in the equal amount, so that we will get the required change in speed, but on the other hand if we transfer this rate of change in speed to the straight cone, that we see that we need to change the speed or we need to shift the cone belt in an unequal manner. So, in the first layer at the first layer the speed reduction should be highest at the rate, and as we progress the reduction will be reduced, and that is not possible with a normal type of the normal equal belt shift. For that we need unequal belt shift. So, that is done by one cam arrangement that we will discuss. So, hyperbolic surface is actually ideal, but there are some technical issues. So, first problem is that it is difficult to design. Then belts always move on surface of varying inclination, that is important. So, if at every point you will see the inclination change, the curvature changes. So, belt always will have differential stress continuously. So, that will actually damage the belt. So, mostly straight sided belts are used in most of the machines, in modern machine. So, with eccentric arrangement, this is the eccentric cam arrangement and this eccentric arrangement ensures the unequal shifting of cone belt to get the required required change in the bobbin speed. So, shift of cone belt is actually building motion's first function is the to shift the cone belt, second is the reversing the direction of the bobbin, and third one is the shortening the lift after every year. So, after every layer the shortening of shift should be there, that we should have, so that we can have tapered end. To form a tapered end on the bobbin, all these changes depend on the roving diameter. So, that how the belt will shift, what will be the rate of shift of belt, and how the reversal, how frequently the reversal will take place, and what will be the shortening, that is a tapered angle. So, everything depends on the roving diameter. So, most of the movement changes by in the modern roving frame by electro-pneumatic arrangement. So, you can see here this is one simple arrangement, bracket is there, the consist of metal brackets 3 and 7, this is 3 and 7. So, this is a simple bracket which is shown in blue color, and rods 5 and 6, these are the rods 5 and 6, and this angle of this rod are actually that it reflects in the taper angle. Whole mechanism is fixed on bobbin rail. We are not going to discuss this machine mechanism, but here this mechanism is there, that it is a bobbin in the whole mechanism. This mechanism is actually fitted on the bobbin rail and moves up and down along with the bobbin rail. Now, there is a plug, electronic plug, so moves up and down. So, this electronic plug is there. When it is moving at the extreme up or extreme low, the plug strikes this rod 3, 5 and 6. So, stationary pin struck one of the rods 5 and 6, and it emits some signal. Okay. So, this 5 and 6, and here it emits signal either by 5 or 6, they are connected with this pneumatic cylinder. Okay. So, this is suppose connected with the C5 and this is connected with 6, and they are getting excited, they get signal, and this is with the 6. Micro switch emits pulse, and each of the pulse operates a release mechanism. So, this is the release mechanism here, release mechanism, release of the belt mechanism. So, the belt is connected with that cone belt rope, it will release the rope, or it will release this is the ratchet mechanism. Ratchet will be released by half tooth. So, half tooth release will be there, and that will allow the shifting. So, what happened, this is a double acting cylinder, these 2 double acting cylinders are there, and depending on the pressure, this piston moves right and to and fro movement is there, and depending on that there will be a release arrangement. So, which is actually this is the release arrangement. Now, it rotates the ratchet by half tooth. Half tooth rotation will be there, because the ratchet mechanism is connected with this is for with the eccentric arrangement, and there is a rope will be there. Rope always actually it's connected with the heavy mass, heavy weight, and that will try to pull, but this stop arrangement will restrict the movement, free movement of the ratchet. So, that is how the belt shifting is controlled. So, after every traverse one release will be there, that means it will rotate by half tooth. So, and that will this half tooth rotation will ensure the cone belt shift. Now, this is rotating by the ratchet is rotating by half tooth, but as it is connected with the eccentric arrangement, due to this eccentric design, the shifting of cone belt will be different after every layer. So, initially the shifting will be maximum, because this is in the maximum diameter, highest diameter, but due to this cam design the diameter gradually reduces. So, that the cone is actually the shifting will be gradually reducing. The throughout the whole build up, typically this eccentric rotates about say 2 full rotation about 720 degree, that we will discuss in the subsequent session. So, this is the ratchet and here is the eccentric arrangement. So, initial shifting you can see W1 it is a maximum shifting, then gradually this shifting increases reduces. Okay. Now, coming to the actual cone belt shifting here. Now, this is by ratchet wheel, here is the ratchet wheel and here this is a cam and cord is arranged, cord is attached and here this is the weight. Now, if there is no restriction, what will happen? The ratchet will or cam will move have free movement. So, this belt will simply shift from left to right. So, there will not be any control. So, for control to restrict the free movement, we have the ratchet stop mechanism, ratchet mechanism. So, rotates by half tooth on each changeover, moves the belt guide through. So, belt guide will move, which will result the movement of belt, shifting of belt. So, gear, eccentric and rope arrangements are there. Weight exerts force, which helps the to pull the guide, belt guide. Ratchet wheel to restrict and controls the movement. So, that ratchet's function is to restrict and controls the movement. Suppose we want to have smaller movement. So, what we have to do? We have to increase the number of teeth. So, smaller movement is will be there, depends on the roving thickness. So, if the roving thickness is reduced, so we need higher number of teeth in the ratchet wheel. The belt moves back after doffing. So, up to the doffing. So, it starts from the left, then goes to the right side, when at this side the its full bobbin is there, full bobbin, and when this is completed, then the belt will be shifted back to the original position automatically by using the motor. Now, this is the photograph of a machine. Here this is the eccentric arrangement and you can see this is the starting point. Starting point, the diameter is maximum. So, gradually the diameter, so that distance from the center is maximum, the radius, that is the effective radius at the start is maximum, then gradually the effective radius reduces. You can see it reduces gradually. So, at the end this will be minimum. So, that is why minimum distance means minimum shift. When we have the ratchet release of ratchet of certain angle. So, every shift typically 1 degree release is there, 1 degree angle release is there for every shift typically. Okay. So, for minor adjustment of belt movement, the ratchet has got limitation. So, we cannot have very high number of teeth in the ratchet. So, for minor adjustment what do? We use the correction rail. Correction rail is there, and typically when ratchet releases the cord or rope, so it will have certain movement, but if the rail is at inclined, so effective shift will be reduced. So, if we need, the roller runs on a correction rail, it is a rail is there, and depending on the angle. So, the actual release is there. Suppose let me tell you, this is a suppose correction rail and here is a roller, this is a release mechanism. So, for x release, if there is a 0 angle, so there will be x movement of the cone belt, x movement, but if the correction rail is at angle theta, so for x release, release is x, that x is released. So, the actual shift of the cone belt will be this much amount, okay, which is nothing but x cos theta. So, actual release will be, so x dash will be x cos theta. So, we can change. So, if we shift this with the help of this screw, if we lift it, okay, then accordingly the shift will be adjusted. So, for minor adjustment, when ratchet wheel is not able to do that, so we use the correction rail. This is the correction rail here. So, belt shifts the rope, that is the belt shifting rope guide is around this roller, okay, guided around this roller. The other side is lifted upward by the screw, as I have mentioned, and where this movement, this is A2 height is more than this is the A1. So, that depending on that angle, the shift can be adjusted. So, release of rope determined by the builder motion is not transferred completely to the belt guide. So, whatever rope is released, but that is not transferred, and which is transferred is that x is released and its transferred is x cos theta, that is actual, the y is the actual shift of the cone belt. So, shifting is smaller, tension variation as bobbin build, that is also there. So, initially the bobbin that initially when the empty bobbin is there, that is on a plastic bobbin, the roving is winding for first layer or for first few layers. What happened? This is the hard package. So, roving tension will be high. On the other hand, when it becomes a larger size, the roving package is softer, so tension will reduce. So, for that also we can have multiple portion, we can divide the correction rail into the multiple portion, so that the shift at different zone also can be controlled. So, initially on hard bobbin and then on the softer bobbin. correction rails are, that is why it is in parts. So, adjust relative to each other. So, we can adjust. So, correction rail what we have discussed is in the, say it is a certain angle, so, to reduce the shift of the cone belt, but this correction rail also can be adjusted at different angle. So, this is theta 1, theta 2, theta 3, depending on our requirement. How fast, how do we want to change the belt shift, that also can be controlled, but in our at present condition, in our derivation we will discuss the simplified model. Tension level can be adjusted from the beginning to end by raising or lowering the individual rail section. So, we can have multiple rail section that we can do by changing the height of the rails, that the angle of the rail. Now, what are the steps to design the cone pulley? Assuming a roving is infinitesimal thickness, the bobbin diameter is dBm corresponding to the winding at various layers of roving, winding RPM Nw for winding each layer of roving of infinitesimal diameter. So, what is a roving winding speed? N B minus N F is the Nw, that is the winding speed. Effectively that speed is used to wind the roving on the bobbin. So, Nw, so we know that V equal to pi dBm to Nb minus Nf. So, this is Nw. So, Nw will be V by pi dBm. So, that is the relationship. We have already discussed this relationship, Nw Nb minus Nf for the bobbin leading mechanism. So, bobbin RPM now. So, bottom cone pulley RPM is N2 RPM for N2M for winding on mth layer. That in the earlier session we have discussed this, we have derived the relationship between the bottom cone pulley RPM and the bobbin RPM, that is from the epicyclic gear section. This derivation we have already done. So, for the given gearing ratio N2M bottom cone pulley RPM is 56785 by 48 is the bare bobbin diameter, empty bobbin diameter, and 2 m minus 1 mth layer, and T is the thickness of the roving. So, gear ratio, gear train ratio from the main shaft to top cone, main shaft to top cone is E. Then top cone pulley NC1 will be Nm is the main shaft pulley speed and E is the gear ratio. So, top cone pulley speed in C1, what is C1? But that is its constant. So, Nm is constant and E is also constant because it is a gear ratio. So, NC1 is the top cone pulley speed, which is always constant. So, you can see here this is the top cone pulley and speed, and here is the bottom cone pulley with the number of layer. Bottom cone pulley speed changes as the belt shift take place. The RPM of top cone pulley is constant. So, that we have already calculated earlier. So, how is it being calculated? So, 827 is the main shaft speed RPM and this is the constant E between the main shaft and the top cone pulley. So, we get 622 RPM. So, assuming there is no slippage. So, we assume effectively there may be some slippage, but if we assume now for the simplicity there is no slippage at the interface between the cone pulleys and the belt, what we get? This is the relationship. What is that? D1 m by D2 m. So, for mth layer, diameter of top cone pulley by diameter of bottom cone pulley equal to, so that is R1 m by R2 m radius ratio and which is equal to N2 m by NC1 which is constant. NC1 is the top cone pulley RPM and at that time what is the RPM of bottom cone pulley? So, N2 m and which is equal to Km. Now, here Km is the factor which is not constant because this one is constant, NC1 is constant, but N21 always reduces with the or 2m reduces with the diameter of the bobbin as with the layer diameter of the bobbin. So, Km also reduces. Okay. So, this is constant top cone drum speed. So, where we can see that d1 by d2 which is k, the value of k is gradually reducing. So, k is variable km. So, we should remember d1 m by d2 m or d r1 m by r2 m is equal to km which is variable. Km is a factor. This km we will be using later. So, therefore, so R1 m equal to km multiplied by R2 m. So, what happened with every shift R1 changes, R1 m changes, km changes and R2 m changes. Here everything are variable, but it is related with R1 m equal to km multiplied by R2 m. So, radio of cone pulleys are R1 m and R2 m values varies with the bobbin diameter. So, both the values vary, that is why km varies. But the condition is here R1 m plus R2 m, although they vary, they are constant. R1 m plus R2 m, their summation will be constant because the belt length is constant and their axes are parallel. Okay, they have the parallel axis shaft. So, the diameter radius of these two will be always summation will be constant because we are using the constant belt length that has to be maintained. K0 is a constant by design, the cone drum shafts are parallel to each other. So, that is how this must be constant. Length of the belt moves over the pulley is fixed. So, other if it is not constant, these are not constant, K0 is not constant, then the length will not be actually the belt, we cannot design a belt. Okay. Belt will always be stretching or relaxing. The sum of the cone pulley radius is around 160 or 165, that we can maintain. So, I think we can consider 165 also, okay. That we will see. So, radius of the bottom cone pulley is, so with respect to the number of layer would be found. So, that from the relationship that Rm R1m equal to Km R2m, this is one relationship, and another relationship is R1m plus R2m equal to K0. So, by using these two relationship we can get R2m equal to K0 by Km plus 1. So, what we do, you just replace this one here. So, Km R2m plus R2m equal to K0. So, replacing this with this value. Okay. So, what we are doing, R2m Km plus 1 equal to K0. So, R2m equal to K0 by Km plus 1. So, from this we can get the value of R2m in terms of K0 and Km, where Km is not constant, Km reduces this. So, we can calculate if we know the R2m, if we know the Km at for a particular value for particular layer. So, R1m will be calculated by substituting the value of R2m in this relationship that we have calculated. So, R1m we can calculate here now. So, what will be there? So, R1m we can use here, we can use the R2m value. So, that we can calculate the R1m also. So, mark the R1m and R2m. So, radius of the cones from the axis of both the cones of the cumulative for the cumulative belt shift Lm. So, what we do? So, we calculate the R1m and R2m. So, we mark for a particular this R1m and R2m we mark from the axis of the both cones for cumulative shift of belt Lm. So, we can calculate the shift. So, these are the types of cone belt: hyperbolic cone, which is not in use due to some technical problems. So, that design problem that we have discussed. Straight cones are nowadays used with the eccentric arrangement. Now, straight cones, why do we use the straight cones? Because hyperbolic cone pulleys are difficult to design, that we have already discussed. Lower winding rate of hyperbolic pulleys, because if we use the hyperbolic pulley, there is a chance of the slippage. So, that is why we use the straight pulley. Belt always moves, okay, over the varying surface. During initial shifting of the belt, the inclination of cone surface is much sharper and belt envelopes large diameter of the pulley, okay, much sharper, because this is the cone pulley diameter. So, here it is a much sharper change. Okay. So, straight cone pulleys are preferred. So, belt length is fixed. So, R1m plus R2m equal to K0. So, maximum and minimum radii R max and R min are also fixed. So, in this case maximum and minimum diameters are fixed. for both top and cone bottom cone pulleys. The total length of pulley is also fixed. So, from there we can calculate the conicity. Okay. So, the taper angle of the cone is related to the maximum and minimum radius and the length of the cone. So, from there maximum and minimum length diameter and the length of the cone, we can calculate the tan gamma will be R max minus R minimum divided by length of the cone. So, this is constant. So, R maximum radius is constant, minimum radius is constant and belt length is constant. So, the angle of taper is constant. So, angle of taper can be calculated by using this relationship. So, we have discussed the basics of the cone pulley. Now, we will discuss the. So, if you see the actual value of a machine is taken, its taper angle is coming out to 5.2 degree standard tapered angle. So, that we will be using in the calculation. So, tan gamma is 0.09123, okay, that is a slope of the pulley. So, now we will discuss the shifting of belt along the cone pulley, which is very important. We will do the detailed calculation here. Okay. Now, radius of top and bottom cone pulley, as we have discussed, R1m and R2m must always be it is varying from their initial value after completion of each layer of winding. So, that is actually that R1m and 1,2m. So, tan gamma equal to R maximum minus R minimum divided by length of the cone pulley. So, total shift of belt Lm for mth layer. So, there are for first layer it is L1, second layer L2, for mth layer general Lm layer, because gradually it will shift. Okay. For mth layer from the initial position along the axis of the pulley. So, initially there will be 0 shifting, then for first layer it is L1. In this way gradually there will be shifting. So, for mth layer it is Lm winding the second layer of roving the arbitrary thickness. So, m onwards m2, 3, 4. So, in this way the shifting will continue and the layering will take place. So, for first layer, so for any that from this relationship, so L1m equal to L11 minus Lm tan gamma. So, L1m is nothing but the, you can see here, this is the L1m. Okay. L1m is the maximum radius for the top cone drum, and as we go on increasing the layer. So, for that for first layer it will be basically L11 LR11. So, this is the minimum maximum radius for the first layer of the top cone pulley, and gradually if we change the shift, belt is shifted, that is Lm, if it increases gradually, initially for first layer Lm is 0, that means R11 will be equal to R11, and but if it is a second layer R12, then there will be shifting. So, this value, so gradually this value will reduces, that means R will reduce for top layer, and for bottom layer it will be this R11 means the top cone. For bottom cone drum R2m will be initially, which is actually minimum radius, R21 is the minimum radius. So, that is the minimum radius plus, so it will be gradually increasing, that is why it is plus sign Lm tan gamma. So, for top cone pulley the radius changes like R11 minus Lm tan gamma. For bottom cone pulley it is changing like R21 plus Lm tan gamma. So, R11 and R21 are the radii of top and bottom cone pulley, while the winding at the first layer of winding. And this one we have already seen. Now, these are decided as per the value of Km obtained. So, R11 by R21. So, R11 by R21, as we know, it is for first layer Km is the, it is equal to Km, as we know Km reduces with the shifting of cone belt. So, R11 by R21 is nothing but R N21 by N1C. N1C means the speed of the RPM of the top cone pulley. This is the top cone pulley RPM, but N21 is the RPM of the bottom cone pulley for the first layer. For the first layer. So, Km is variable. So, N21 is the RPM of bottom cone pulley while winding the first layer of roving on the bare bobbin. Angular velocity of top cone pulley is fixed, it is given by the gearing plan, and adding these two. So, R1m plus R2m, if we add we get K0, K0 is 165, let us assume for the as per the design 165. So, R2m plus R1m is always constant equal to K0 equal to 165. So, this is the actual addition of the radius which is constant K0. Now, for this is for the top cone pulley and this is for the bottom cone pulley. Top cone pulley RPM is fixed. Okay. So, subtracting the equations Rm1 and Rm2 and substituting the K equal to K0 equal to 165. Let us see R2m plus minus R1m. So, R1m R2m, what we are getting, the R21 minus R11 and then plus 2 Lm tan gamma. So, this, so R2m minus R1m, we are getting this relationship. Now, the value of tan gamma, as we know, for the standard machine it is a 0.09123, that we have seen earlier. For the taper angle of 5.2, that is constant. Now, Lm, so here Lm equal to R2m minus R1m minus R2m plus R11 divided by 2 multiplied by, this is nothing but 2 multiplied by 0.09123. So, that from there we get this relationship. Initial values of R11 and R21 are 108 and 57. So, that we are getting the value 165 approximately. Okay. So, R max for top cone and R minimum for bottom cone. So, bottom cone will start at the minimum diameter, this is R minimum and R maximum. What is LM? LM from winding second layer and arbitrary layer will be, this is the LM. So, what we are getting R 21 R 11 minus R 21, we are getting the 51. So, R 11 this minus 57, we are getting 51. So, this is the relationship. So, this is for the second layer onward, and we have already derived this relationship R, say N2M equal to 56785 divided by 48 bare bobbin diameter, 2 m is the mth layer and T is the thickness of the roving. So, from these two relationship what we get, so where m varies from 2, 3, 4 to m. So, profile of the, so what we got the two relationship, from these two relationships we can calculate the shift of the cone belt. So, profile of shifting of the belt along the axis of straight and hyperbolic cone for extreme left end of the cone. Okay. Now, cumulative axis shift and the axial shift of the belt from, for both the cases, that is in hyperbolic and the straight pulleys, from the extreme left end we can, this is the plotting. Now, if you see for hyperbolic cone pulley, so we shift the cone belt in a straight fashion. So, for every layer the shifting will be equal, but for the straight cone we have to shift the belt in such a fashion, initially with a number of layers the shifting will be maximum highest at highest rate, gradually it will reduce. So, this shifting, this is done by using the eccentric arrangement. So, the shifting of the belt is uniform for the hyperbolic one, okay, and the for the latter, that is for the straight cone, the shifts are longer at the beginning, that longer at the beginning of winding and then progressively reduces. So, there will be hyperbolic shift, hyperbolic change in the shift. So, this is done by the eccentric arrangement. You can see, and depends on the change in pattern, changing pattern of R1m and R2m. How the R1m, R2m changes? So, that is we have seen km. So, this shift will be actually a function of km, how the km is changing for the straight type cone. Now, for calculating the belt shift, the correction for belt shift, so belt slippage, the correction can be done. So, amount of slippage, the belt slip, say let us see it is S% over the cone pulley. Now, here if it is S%, so we are doing the corrections. So, N1 is the RPM of top cone pulley. See N1 by N2 as we know. So, R2 by R1 we know that is the condition. So, N1 by and it is 1 by KMC Km. Now, for correction if we try to incorporate normal case it would have been like this. N1 N2m by Rm R2m by R1m, okay. N1m is equal to. So, here N1m N2m, just this will be basically N1m by N2m. This is mixed, some mistake is there. So, this will be there N1m by N2m. So, R2m will 1 by Km, that was the normal relationship here. Now, here we can see that due to the slippage we are using the R2mc by R1mc. So, that is how we change the speed. So, suffix C stands for the corrected value, KMC is more than Km and R1mc is more than R1m and R2mc is less than R2m. So, after correction this is to be maintained. So, how are you maintaining the for to actually counteract the belt slippage, the belt must be moved towards the starting point. So, towards the left side we shift of the cone pulley by some distance to get the right ratio of the top and bottom pulley. So, there is a slippage for a particular layer to maintain the speed. So, we have to shift the cone belt little bit on the left side starting towards the starting side. So, that is the relationship, the belt must be moved towards the starting side of the cone belt to some distance for to maintain the ratio. Now, considering the belt slippage is 3%, quite normal, we consider the radius of the top and bottom cone pulley should be adjusted to 106 millimeter and 58.7 millimeter. So, that 106.3 millimeter. So, that is a little bit adjustment has to be made manually, okay, and where the bare bobbin diameter is 48 millimeter. So, that is assuming there is a approximately 3% slippage. So, it may not be always correct. So, that little bit trial and error can be done. So, initial value was instead of 1808 106.3 we can do, and for 57 instead of 57 we can make it say 58.7. So, then the relationship as we have already derived this Lm will become this one. So, 106.3 minus, so this is it was earlier 51, now it will become 47.6. Okay. So, because 106.3 minus 58.7 it will be 47.6. Now, profile of shifting the belt with 3% of cone pulley from the starting position corresponding to the winding of the empty, total shift will be 570 millimeter, that is the profile. Total shift will be 570 millimeter. Now, cam device. Now, cam device is used, that is eccentric arrangement is used for actually to have the cone belt shift at different extent. To starting at the starting point there will be larger shift, but as it goes on. So, as we have seen, this type of shift is there, this is a shift, this is the number of layer. So, number of layers. So, shifting initially will be very high. So, that is done by, this is the cam arrangement. Now, let us see how is it is taking place. Now, cam rotates its clockwise direction. As the cam rotates clockwise direction, gradually the radius, effective radius reduces from the maximum, this is the maximum point, then gradually reduces toward the minimum length, and every time, every layer, it is a small changes will be the same, 1 degree theta becomes at the end of each layer of roving. So, after every layer the cam rotates by 1 degree due to the release of the ratchet release mechanism. Release the cord and shifting the belt so that the required diameter of cones are selected to maintain the required bobbin speed. Okay. This is the cord, and here is the shifting takes place, and this cam arrangement is shown here. Okay. This is the belt shifting. This reduces the rotational speed of winding gradually, which we want. Degree of rotation of cam can be controlled by ratchet wheel. So, how much we want to release, that is controlled by ratchet wheel, and typically let us assume it is 1 degree per release. Now, try to see, this is the cam release mechanism. Initial radius, first layer, it is R1. Gradually the radius changes, R2, R3, it is becoming smaller and smaller. This is the R1 maximum, this is R1. Then when it shifts by 1 degree, this is say 1 degree, the radius becomes R2, then R3, R4, every degree release there will be, the radius will be reducing gradually. So, rotation of cam in radians theta for each layer of roving is very small, that 1 degree. So, we can convert it to radian, it will be very small. The peripheral length of cam and the corresponding length of the cord, when the cam rotates by theta degree, that peripheral length of cam is S2 triple dash, that is we can for the second layer, S2 triple dash is for winding the second layer of the roving. So, initial radius is R1, radius of cam R2 after rotation of theta degree. So, it is R2, this is after theta degree, it has become R2, that is for the first layer. for the next layer it is R2. So, that S, the peripheral distance S2 triple dash will be r theta, basically radius multiplied by the radian of the angle release. We know this r theta, this is the basically this radius multiplied by radian. Length of the cord from the tip of the cam. So, from this tip of the cam, here is the tip of the cam and the apex point of the roller, this apex point of the roller for the first layer is S1. So, that is the S1 for the first layer. Length of the cord during the winding of the second layer is S2. So, vertical distance between the apex point of the roller and the cam. So, vertical distance is it is from H1 to H2. So, H1 to H2, this is H2 is the vertical distance, here that will be vertical distance shifting. So, initially it was H1 and then H2. So, that will be basically H2 is nothing but H1 plus R1 minus R2. So, H1 plus this distance, So, H1 is this one plus this distance. What is this distance? It is R1 minus R2. So, H1 plus R1 minus R2 is the H2, this is H2. Okay. Then the path length of the cord S2 dash will be, that is the path length S2 dash will be this, okay. This is S2 dash will be this plus L square, okay. This is the L. So, under root H2 square. So, S2 double dash will be underscore H2 square plus L square, L square. H2 square plus L square. So, this is L and this one is A. So, S2 dash this distance we can calculate by this. So, S2 dash is calculated, this is the S2 dash, can change the color. S2 dash is calculated by using this formula. The actual length of cord released, that means S2 dash, so this is S2 double dash, okay, this distance. So, the actual length of the cord released S2 dash at the beginning of winding second layer of roving will be that it is correspond to the belt shift S2 are related as this one. S2 3, that is the peripheral distance, minus S2 dash by S1 double dash, S2 dash minus S1 double dash equal to S2 dash. So, this is the peripheral distance released. So, it will be nothing but S2 by cos gamma. Gamma is the this angle of inclination. The above equation can be rewritten as this is the above equation. Now, what we have done, this is equal to this, that we have the peripheral distance minus this distance we have already done, that is S2 dash, and that is the that we have done S2 double dash minus S1 double dash, that is the change, plus S1 double dash, okay, equal to S2 dash, that is equal to S2 by cos gamma. So, from this equation what we can get is, this is the equation. In the above equation R1 this is the R1 maximum distance, H, this is the H that can be, maximum distance is known, H is known, L can be calculated, S2 is known, and cos gamma and S double dash. So, all these things are known. When theta is very small, so 1 degree, the unknown parameter R2 can be solved. So, for very small theta, shifting, that R2 is the unknown parameter, because maximum distance is known. So, we need to know the shifting. So, for that we have to define the cone profile, so that is a cam profile. So, that is why R2 is known for that, unknown for that theta degree. So, shifting of cord and belt requires at the beginning of winding of third layer of the roving can be written as, this is written as, you can see that this is for R2 was for R1 or R2 are for second layer. So, for third layer R2 R3 by 2, and H will be, this is the maximum height, that is starting height. So, R1 and R2 will become R3 for the third layer, and this will become S2 dash and S3, S2 double dash, S3 dash will be there, and it will be in place of S2, it will be S3 by cos gamma. So, in this way for every layer we can calculate. So, for third layer this is the relationship. So, radius of cam. So, our idea is to define the cam radius. So, radius of cam while winding the third layer R3 can be found as a value of S3 is known. So, R3 we can calculate, that is the radius of cam when S3 is known. So, radius of cam corresponding to the angle of rotation can be calculated to generate the complete profile of the cam. So, R1, R2, R3. So, if we can keep on calculating, okay. So, we can generate the complete profile for a particular design and how the shifting can be performed. So, if the cam profile is to be generated for 720 degree. So, we want to generate for 2 complete rotation. So, 720 degree roving thickness is T can be found from the maximum and minimum diameter of the bobbin. So, D max and D minimum that we have already discussed. So, by this formula, so if we know the maximum diameter of roving and minimum diameter of roving and number of layers, though we are designing the cone profile for 720 degrees. So, the number of layer will be 720. So, m will be 720. So, here we can calculate the T value, what will be the thickness of roving for this type of design. So, number of shifts of belt. So, belt will be shifting after every 1 degree revolution. So, there will be 720 steps of shifting. So, would be, so 720 with 1 degree angular rotation of cam for each layer of roving. The thickness of the roving would be 0.085. So, 85 micron. So, how are you getting 85 micron here? So, basically that will be that is 85 micron. So, 720 steps. If the minimum and maximum diameters of the bobbin are 48 and 170 millimeter. So, minimum diameter of bobbin is 48 and maximum diameter is 170 millimeter, and for that what we can get, and this there will be 720 layers, 720 layers. So, you can see that 170 minus 48, that the diameter, and radius difference will be divided by 2, and if we divide by 720 and considering that the roving is incompressible. So, the roving diameter will be roughly 0.085 millimeter. So, this is coming from this relationship with this assumption. So, 720 times the layers will be there. Now, this is the design. So, you can see the design here, maximum radius R1, this is R1 and R2, R3, R4, in this way it will change. You can see there are total complete 2 cycle, this is 360 degree and from there it is 360 degree. So, the cam is designed for complete 720 degree rotation. You can see this is the cam, the belt shifts by distance Sm. So, this belt shifts by the distance Sm during the winding of mth layer is Lm minus Lm minus. So, for mth layer how much the belt will shift. So, belt shift reduces gradually. So, Lm minus Lm minus 1. So, distance moved by the roller belt guide is compensated by compensating rail is S dash m, release of the cord. So, S dash m will be equal to Sm by cos gamma. Now, we can see this is the system here. Now, initially for different layer the shifting is there. In the first layer of winding, diameter of cam is the maximum and decreases progressively towards the end, that we have already discussed. Working length of the cone is 570 millimeter and cam can be designed to have 570 radial length. So, R1, R2, R3 corresponding to 570 degree rotation, to have fine adjustment. So, that also we can design. So, instead of 720 degree we can have 570 degree design of cam to adjust the cone length of 570 millimeter. Path length of cord between the guide and cam. So, guide and cam, that is the path length. So, is double dash m. So, this is the cam and the path length, and this is the guide and this is the cam. Between the guide and cam, this length is double dash m progressively increases from initial layer to the final layer, gradually it increases. Okay. So, you can see S double dash 1 m minus 1 m. So, with every layer it increases. So, circumferential length of the cam R 1 to R 2 and R 2 to R 3 in that way denotes that S m triple dash progressively decreases because of the effective radius of the cam. S dash m is the difference in circumferential length and difference in link length S double dash. So, this is the link length and circumferential length. So, the difference will be the S dash m. The shifting of belt S m reduces from the second to last winding layer. So, S m is basically this reduces from the second to last layer. So, S, this is the circumferential length, and here S double dash m minus S double dash m minus 1, that is for mth layer how much shift will be, how much difference will be there, and that is the actual release. Now, we will stop here and we will start. We have completed the roving session. So, we will start the next session, that is we will start a ring frame from the next session. Okay. Thank you.